Hello. Yeah, so I'm really honored to introduce to you the last speaker of the public session, Professor Cumrun Vafa. He's one of the most brilliant theoretical physicists of our times. He combines mathematical intuition and physical insight in quite a remarkable way. And therefore he's made a number of seminal contributions in string theory, in quantum field theory, and mathematics. Together with Andy Strominger, as you just heard, he did the first this landmark calculation on the first microscopic basis for the Bekenstein-Hawking black hole entropy. This is, as Andy said, it puts the enterprise of quantum gravity or string theory on a much firmer footing than we had a couple of decades ago. So I've had the privilege of working with Cumrun, and I would often marvel at the way in which at the lightning speed at which he would combine these various physical and mathematical ideas. And and you can see this as in his contributions. He's been one of the pioneers of mirror symmetry, which combined the ideas of string theory to give completely novel predictions in mathematics, and similarly in topological string theory and F theory and so on and so forth. So I won't go more into those details, but let me just mention for the record that Cumrun did his PhD at Princeton and then went to Harvard as a junior fellow, and he has continued on as a faculty member at Harvard, where he is currently the Donner Professor of Science. And among his significant recognitions are the Dirac Medal in 2008, the AMS Leonard Eisenberg Prize for Maths and Physics, the Frontiers in Physics Breakthrough Prize. He's also a member of the US National Academy of Sciences, etc. So I won't keep you further from Cumrun, and so let me invite Cumrun to give his lecture.
Thank you. Thank you for this very kind introduction. It's a great pleasure to be here in Bangalore and in this context to give a talk about physics and geometry. It's a pleasure for me to be here in India in more broad terms, which I view as the cradle of science and mathematics in the first place. So it's a place I feel honored to give a talk about physics and geometry. So maybe if we can take the light a little down in the front, it'd be easier to see. I don't know if there's a possibility. Thank you. So I'm going to talk about deep connections between geometry and physics, and I will trace some of the links between the two subjects by giving examples. So the two beautiful talks we heard already did quite a fantastic job in actually dealing with much harder problem that I'm going to take on. Mine is just going to be giving examples, and I hope to illustrate in the context of examples some basic principles that have emerged between connecting physics and geometry, and in particular in the context of string theory. Well, we are all familiar with Euclidean geometry, which is where I got interested in geometry. You know, this beautiful Pythagorean theorem, which you can see in beautiful different terms. And of course, geometry and its connection with physics, in the sense that we actually can apply, was very much in the mind of people from long ago. The Greeks were thinking about this when they discovered the fact that the Earth was round, basically by following simple geometry and following the fact what happens about the angles, about the shadows as you move along the Earth, gave them a reasonable estimate of the radius of the Earth. So simple ideas of geometry were already applied in early days into deducing amazing facts like the Earth that we live on is round. The Greeks were very smart. In fact, the way they phrased the way they phrase their understanding of nature is very close to the modern way we think about it. Not only they discovered the Earth was round, they also thought, well, it's round and it's spherical, well, maybe it must be in the center of the universe. So they placed the Earth at the very center of the universe. That's the way they thought about it. And in fact, they tried to use symmetry principles to explain physical facts. So they viewed the Earth in the center of the universe, and they thought the Earth is not moving, and therefore there was a question, why isn't the Earth moving? What keeps it from moving one way or another? And their answer was very elegant. They said, if it were to move, it breaks a symmetry, so it doesn't move. This is very much like the way a modern physicist thinks about symmetry principles. The reason Earth doesn't move is because it's spherical at the center of the universe, and if it were to move, why should it go that way, not the other way? It breaks a symmetry, therefore it stays put. Very elegant thinking. But the Greek philosophers and mathematicians and scientists were actually smarter than this. They continued. Aristotle argued that this is a bad reasoning. How did he argue? He said, well, suppose you're at the center of the universe right there, and around, since it's spherical symmetric, you might have a circle of all possible areas or a spherical area where you have food gathered around you like loaves of bread, but you're in the center of the universe. And time goes on and you get hungry. Are you going to stay put? Well, if you're a philosopher, you might say, I won't go any direction because I will break the symmetry. But we know from experience the answer to the question. You will say, what the heck with the symmetry? I'm going to move, get my loaf of bread. So spontaneous symmetry breaking takes place. This was Aristotle's reasoning about the fact that symmetry principle, powerful as it is, could be spontaneously broken. A few thousand years ago, it's amazing. So he would go and he would get his food. In fact, this explains why our eyes are not spherical symmetric or circularly symmetric around our head. We don't have eyes circularly symmetric, even though that would be the most symmetric situation, because our eyes is towards the food. We only need to direct that way. So in fact, our body reflects the spontaneous symmetry breaking. So these deep facts about physics is ingrained in us, in our bodies, and these principles of connection between symmetry and geometry continues to come to the forefront of our thinking. So we know we look more or less like this. The Greek had other beautiful ideas, the Platonic Solids, beautiful symmetries. So they have combined amazing ideas about symmetries and mathematics to come up with some beautiful objects. And these Platonic solids, they thought it's so elegant that must be underlying some deep principles of physics. And they tried to connect it to some principles of physics, which we now view perhaps wasn't exactly the right way to do it. Nevertheless, they were dealing with beautiful mathematics. And somehow, the question was, what is the good use of these mathematics in reality, in physics? Now I will really push forward in time, very fast forward. There are many interesting things happen in the middle, so I don't want to undermine those, but we don't have time, so I will just quickly come towards more modern times. Galileo is one of the key figures in more modern times, where he was thinking about principles of physics as well. And at his time, there was a question that was posed whether heavier objects and lighter objects fall at the same rate towards the Earth. Aristotle had, of course, argued, of course, the heavier object falls faster because it's heavier. And this did not satisfy Aristotle, who did some experiments, as it's reported, on the Pisa Tower by dropping heavier and lighter objects. But actually, during those days, it was believed to be a dirty thing to do experiments. You don't dirty your hands with experiments. It should be pure thought. So the scientists at that period were much more idealistic. They wanted to think in the mode of thought of Greeks. You have pure reasoning to deduce things. And Aristotle was really, Galileo was really doing these experiments. It was a little beneath their dignity to do it. So Galileo had a hard task to convince his colleagues, so he came up with a theoretical reasoning in addition to his experiments to convince them that it could also be deduced theoretically. And his reasoning, again, was based on symmetry principles. So this idea that symmetries rule physics was amazing. And he thought about the following. He said, suppose I have 3 bricks of exactly the same size, and I drop them. Which one will hit the ground first? Again, this answer to this question is obvious by symmetry. Since they are all the same, symmetry tells you they fall at the same rate. But then he said, now he uses intuition. He says, well, we know from experience that moving the bricks a little to the left or to the right should not affect it. There's a symmetry of movement. So let's move 2 of the bricks and put them next to each other. And let's repeat the experiment. Well, nothing will change because you're doing the same thing again. And they will fall at the same rate again. But he said, this one is now twice bigger than this one in mass. And therefore, we deduce the more massive objects fall at the same rate as lighter objects. So this is, again, combination of symmetry principles with intuition, which explains some deep fact. We push forward to Newton's time. Newton, he did tremendous contribution to physics. And, his idea about the apple and how it led to his theory of gravitation is legendary. We do not know the precise truth about to what extent these details are actually the way he actually discovered gravity. But in his book, Principia Mathematica, one way he actually depicts how he thinks about gravity is quite illuminating and beautiful. And again, it requires no equations to understand. It requires just pure thought in some sense, the same way Galileo's description involved only pure thought. And he thought this is a picture from his book, where he imagines the following scenario. He imagines having the Earth, and there's a mountain on top of there, and you want to go on top of the mountain over there and fire a cannonball. Now, of course, if you fire a cannonball, you think the cannonball will fall down on the Earth somewhere. But then he thought a sequence of these firing of the cannonballs with ever more energy, and the more and more energy it had, the farther it fell down. And then he says, well, if you give it enough kick, it will fall further down. It's trying to fall down, but it kind of keeps missing the Earth, and it comes back to where it was, and this gives you a circular orbit. So he's, in this picture, explaining that the falling down of an object is related to its going in circle. Namely, an object like moon, which is going around the Earth, is actually falling, but it doesn't hit the ground because the Earth keeps turning. So it's a game between the moon and the Earth. Moon is going to try to hit the Earth, but Earth keeps going in circles, so therefore the moon keeps missing it. So this, again, elegant, somewhat poetic way of thinking about what is happening, what does an orbit mean, actually is quite elegant and combines our intuition about the falling object into a complicated-looking thing like an orbit of a moon. Again, a beautiful connection between physics and geometry. So his equations describe even large-scale properties of galaxies and so forth. But in his description, the space is viewed as completely flat and having nothing interesting as properties. But as we heard, in the context of Einstein's theory, the story changes quite a bit. So Einstein taught us that, first of all, we should not just be thinking about space, but we should also combine it with time. We talk about space and time. And in this way, a beautiful geometry of space and time emerges, where we think about space and time as one object, which has a structure because nothing can go faster than speed of light. So at every point, you have some future directions that you can possibly probe, and some past you could have come from, but not other places. So there will be an interesting structure, what we call the causal structure, in the universe. And in addition, this can actually lead quite dramatically to statements which are completely unintuitive based on Pythagorean theorem. So Einstein uses a Pythagorean theorem to prove the fact that if you move, the time appears to slow down relative to somebody who's not moving. And the reasoning is simple, is that if you imagine that you're in a, let's say, a train, and you're bouncing light from the ceiling of the train, from a point of view of an observer who's not moving, the light appears not to go straight up and down, but actually at an angle. Because by the time it hits the ceiling, the train has moved to the right, so it will go at a longer distance. But a longer distance, if this is the speed of light, takes a longer time compared to the light it will take to go from this point to that point. So the outside observer measures the time which is proportional to this length, because it measures the speed of light divided by, from the speed of light and the distance can get the time. But the guy in the train measures the time related to just distance going up and down. Therefore, they measure different distances. So the time dilation is related to Pythagorean theorem that this length is longer than that length. A simple application of geometry combined with an amazing principle that the speed of light is the same for everybody. So if you combine the symmetry principle with a simple geometric fact, you deduce an amazing conclusion, as Einstein did, that time slows down if you're going on a train relative to somebody who's not moving. And as Andy described in beautiful detail, the geometry of space and time is curved in Einstein's theory. And that's how he described, how he geometrized Newton's theory of gravity, in the sense that objects go in geodesics, straight lines, but because the geometry is curved, even though they might start going straight parallel, they might end up getting closer to each other as if they are being pulled together or repelled, depending on what kind of curvature you might have. And as Einstein originally discovered, the light should be bent by passing through massive objects, and this is due to the curvature of space and time. And this was, of course, one of his first early predictions that was verified. And these beautiful lenses that we see, this lensing phenomena is quite well seen and measured. And we now know that this bending of the light has given rise to gravitational lenses, which are quite spectacular. Now I move forward a few decades to closer times, and then come to the discussion of modern application of symmetry breaking. And this was discussed in Natty's talk in the context of the Higgs particle. We think about the Higgs particle as being related to the existence of mass. We say we are made of objects which have mass, and this turns out to be related to a breaking of a symmetry in physics. If you have a particle, if you have a hill like this, and if the hill, if you have a particle here, it won't stay there for long, but because slightest movement of it will drop it down to the bottom of the valley and would be over there. So again, this should remind you of a symmetry that we were discussing in the context of Greek times. Namely, if you start at the center of the universe, the bottom of the valley might have food there. You might want to go down there. And this is very similar to that phenomena, that the particle will roll down to the bottom of the valley. That's where the food is that will go. So it turns out that if you put the particle up there, the analog of that field in that top position, the particles will not have any mass. And the fact that it drops to the bottom here is actually how the particles get mass. Roughly speaking, you can think of it this way. You can think at every point in space as if you have a little invisible hill like this. And there are these particles which are all sitting at the bottom of these valleys. And then a particle would want to go on, but it hits these particles at the bottom of the valleys and pushes in different direction, and thus by picking up masses by this process. So this is a relation between how we view symmetry breaking and particles picking up mass through this process. If this particle was at the top of the valley, it turns out that the particle misses hitting it, and goes straight through as if it has no mass. So this is the sense in which we think about the Higgs particle being related to a phenomena of particles picking up masses. Particle physics has been very successful in describing elementary particles, how they interact and so forth, as Natty beautifully reviewed. And you get beautiful diagrams about what kind of processes can happen, how particles can go from one to the other. And the structure of the interaction involves a bizarre phenomena. A particle can come, and out of the particle, you create another particle. It's completely unintuitive. If you first hear this, you say, where did the other particle come from? It cannot create from nothing. Okay? But in particle physics, we have become so used to this that we don't think this is that strange. One thing comes and something comes out of it, goes somewhere else. It's a bizarre phenomena, but this turns out to be related to the interactions that we understand in the context of particle physics. Particles get created, or if you run it backwards in time, get annihilated this way. Comes along string theory, as you heard in the previous talks, to describe the same bizarre geometrical structure and have a completely different picture about how the interactions take place. You see, the particles are replaced by these little strings, and when they come forward, they hit each other, they make one particle. Or the other way, if your string comes this way, the act of splitting a particle to the other one is this way. If I draw this picture to you, you would not have asked me, where did the other particle come from? Where did it get created from? This picture is self-explanatory. It's part of the same string. It's not bizarre. So in the context of string theory, this bizarre act of creation of particle does not need any explanation. You just draw the picture. The picture says it all. And that's the elegant piece, that the geometry underlies interaction of physics. It is more elegant than particle physics in the sense that it does away with this ad hoc process of creation or annihilation of particle, and geometry explains it by itself. And moreover, the bonus is, as Andy was mentioning, that the particles get unified into one object, this string. You can have all these different properties of the string encode different particles. So some features are still surprising, and a new way symmetry breaking is realized. In fact, the theme of my talk has been to emphasize symmetry principle and the fact that the symmetries can be broken. String theory brings a new way in which symmetry can be broken. You see, if you look at the space, extended in all these different directions, they all look symmetric. If you go that way or that way and so forth, if you forget about the Earth, it looks all the same. It should all look the same. You can go in different directions. But in string theory, we have actually found that if string theory is actually a theory of our universe, it better have a way that the symmetry is naturally broken. Namely, different directions look different. Namely, one direction, if you go farther back, you might come back to yourself. Whereas if you go the other way, you may not come back to yourself the same way. Or it might be much longer. So in other words, you break the symmetry between different directions. More precisely, we think that the directions in which we usually think about as space, like three-dimensional space, is of course very large, but there are additional directions in space which are tiny, which is microscopic, and it's not easy to measure because they're so tiny, even with very fine microscopes, we cannot see them. Therefore, this space itself has broken symmetry spontaneously. Somehow the symmetry that we started with is not the symmetry that we end up with. So we think about having 3 spatial directions, which is much longer than the other 6 directions that we have. In fact, we have 6 additional spatial directions, which here, for simplicity, I'm drawing as if it's one-dimensional. So I'm thinking about the one-dimensional circle here versus one-dimensional length here. You can imagine that you multiply this by 6 factors and this by 3 factors to get what we think might be a good model of our universe in string theory. More precisely, you can think about at every point in our space, if you really think about this plane here as a 2-dimensional slice of our universe, at each point you have these tiny little spheres attached. They're so tiny you cannot see them. But this sounds a little ad hoc. It looks a little ad hoc. It's looked like we are hiding something in these dimensions, and we're throwing them away from the theory. It doesn't look very satisfactory. The question would become, what are the extra dimensions good for? We could accommodate them in the theory as some kind of a spontaneous symmetry breaking, but that's trying to get rid of them. That trying to get rid of them is not nice. What good are they? Enters this question of black hole, which Andy mentioned and described beautifully. There are these holes in space, and as he reviewed, the Bekenstein and Hawking's contribution in this context related to one amazing fact, that they seem to have internal degrees of freedom proportional to the exponential of the area of the black hole measured in Planck units, divided by 4. And this is an amazingly huge entropy. And the question is, where are they? And what constitutes these degrees of freedom? And string theory has found an interesting answer to this question, that the degrees of freedom of the black hole seem to be hiding in these extra dimensions, which were embarrassing to string theorists. That you can actually use these string theories to find how the degrees of freedom of black hole can be constituted. So in fact, you can have a model of this. You can think about this point in space and think about these as extra dimensions in string theory. And you imagine wrapping strings or some membranes, which are part of the degrees of freedom of string theory, around these. And if you wrap more and more of these, you get a more and more massive object down here. So in fact, if you have a lot of them, you can deform the shape of the space. Let me see if I can manage. Okay, so as you can see, as we saw, so again, so by wrapping more and more of these membranes, you actually get a black hole with some horizon area near there. So then the question is, what are the degrees of freedom? Well, the more you wrap, the more you get a black hole. But how many ways are there of wrapping it? You can count. You begin to count how many ways you can wrap. And counting, and as we did with Andy, counting these degrees of freedom led to the prediction about the relation between those counts and the area of the horizon. So again, geometry comes to answer a question about physics. So I was mentioning about the fact that the dimension of the space is more than 3. That's already quite amazing and dramatic. But string theory does much more amazing stuff. That was just the tip of the iceberg. So here I'm going to review some other aspects of geometry which has been modified that we have learned in string theory. First of all, duality symmetries. That different looking physical system can be identical. This is something that Natty also mentioned, that we can have two very different looking things which are nevertheless, they are the same. And this is, I think, beautifully illustrated by this drawing of Escher. You see, if you look at each corner of this drawing, it looks like a nice story going on. You know, the birds flying, the dark birds. Here the white birds are flying, and it's night. And here you have the day, and here you have the night, and if you have a field. But if you look all over, it looks like a coherent story. There's a coherent drawing. If you just knew about this corner of it, you would not have anticipated that these fields over here have anything to do with these birds up there. But this drawing, they say, in some sense, says that they are the same story. This is very much a caricature of what we have been discovering in modern days in the context of string theory. We usually study some corner which looks much more simpler story, but actually you can move over and to different corners and get different pieces of the picture emerging. And this we say duality. This is what we mean by duality in the context of string theory. And it has led to pieces that actually surprise us, because what is true in one corner of that drawing might look like it's wrong in another corner, but they are continuously related to each other. For example, we can ask, is the dimension of space an invariant concept? Can we actually say the dimension is such and such? And actually, we have learned that that's not the case, because this dimension could be hiding along another direction. It might be too small for you to measure. So there might be some other dimension opening up. You could ask, is the diameter of this space, if you measuring the length with a ruler, is that an invariant notion? Does everybody agree what the length of a space is? So for example, if you have a circle, if you send the light around and you measure how long it takes to come back, you multiply by the speed of light, you get the length of the diameter. So you say, of course, I stand over here, send the light beam, and measure how long it takes to go around the circle. That's going to give me the diameter. So everybody should agree because the speed of light is the same for everybody. So there cannot be no disagreement about the diameter of a space. Well, it turns out that in string theory, we have found that in a different frame, in different corner of this drawing, the same circle can be represented by a circle with inverse the radius in string units. And what appears as a light on one side, appears as a different kind of light on the other side. So whereas one light measure radius r here, it will measure radius opposite to 1 over r for the other guy, and so forth. So the notion of distance is not a duality invariant concept. Is topology of the space an invariant concept? What is the topology of the space? How many holes does it have? How many handles does it have? Count, there's this hole, that hole, just count them. Does everybody agree with the number of holes a space might have? The answer is no. That different corners of this drawing might depict the same space with one topology and another space with a different topology, which are nevertheless identical in physical properties. This is an example called mirror symmetry, for example, is of this type. Two different geometries which are totally different, every mathematician would agree they are different, will lead to giving the same physical system. Quite remarkable. And geometry also plays an important role in string theory in terms of its role as building blocks for matter. We know particles in the context of string theory is replaced by strings, but we actually learned that that's not the end of the story. The string can sometimes be viewed as membranes, like higher dimensional objects themselves, or even more exotic higher dimensional objects. Higher dimensional geometries, and they could be part of this, they are part of this theory. So there is geometry already coming through the object themselves, the matter. The matter are just not boring point-like. They could have interesting structure themselves. And in fact, they could have different properties, like one could end on the other guy. And so you can play all these kind of games with matter itself as very much geometric. Can geometry mimic forces other than gravity? We already said that geometry plays the role of gravity. It geometrizes Newton's gravity, but actually geometry can do much more. Geometry turns out it can also mimic regular forces, like the forces that we are familiar with as like strong forces that we are familiar for nuclear physics and all that, can actually be geometrically realized. So geometry can mimic those forces. So one way we know in the context of Einstein's theory is that if you put, for example, some kind of a cosmic string at some point, what it will do is that if the light goes, it kind of bends it because the space actually looks like a cone. You delete a kind of a pi wedge here, and you glue it together so you get a conical shape. And the light, when it wants to go straight, it kind of bends because it's like a cone. And this is the effect of having matter here. This is something that we understand in the context of Einstein's theory. But what turns out to be true in the context of string theory is that if you take pairs of these cones and put them together, the cone will have a higher dimensional geometry. On that singular apex of the cone, or that region, lies new forces. So it turns out this extension of these cone singularities lead to forces which live in that apex of the cone, which actually turn out to be related to Platonic solids. So the same Platonic solids that showed up for the Greek geometers makes a comeback in modern days as being actually related to the origin of forces in the context of string theory. Not in the way they envisioned, but nevertheless, the elegance of the mathematics pops out again in this context. You can ask the inverse question. Can gauge forces mimic geometry? Can you reverse the role and think about it? Well, it's natural to think that should also be possible. And indeed, this is related to a beautiful development called holography, where you can, the simplest version of it is a situation where you have you basically take electromagnetic type forces, a little bit more complicated version, and in 4 dimensions, it turns out to be mimicking gravity in one higher dimension. This is what Andy also mentioned in the context of what's called holography. So you have something which is living on the boundary of this space, some gauge forces like particles which interact similar to electromagnetic forces, mimic gravity in one higher dimensions. And it turns out that the geometric transitions play a key role here. You think about having objects which lie on some region, and these membranes pull the space so that this becomes singular, and then a different channel opens up, and you get flux coming out in the other way. So there's a beautiful geometry underlying these holographic systems. Let me conclude. I'm sure it has been a long day for you. Geometry and physics have a long and exciting mutual history, and we have witnessed that in the context of string theory, this interaction has amplified quite a bit. Thank you.
Thank you very much, Cumrun, for that electrifying talk. So questions? So over there in the middle.
Space and dimensions of space. So, but what exactly is space, sir? Can you please elaborate on that?
Well, part of the statement, it's a good question, and part of what I was trying to convey is that we now know that there is no such natural definition of space. Space, in a sense, is an emergent concept in the context of string theory. If its dimension cannot be mentioned, if its topology cannot be mentioned, if its diameter cannot be mentioned in an invariant way, that means that the notion of space is kind of dependent on what you mean by it. So there's no invariant definition of the notion of what is space. We know how it can be emergent in some ways, and we know what it means to have a space. Once you give me a definition, things can move on it, etc. Something should mimic that property. Then we say, oh, we have an approximate notion of space. But an absolute definition of it doesn't exist.
And also for time, sir, don't we...
The mic is not working? Okay.
Hello?
Yeah.
Yeah. We use time to measure like changes around us. How does it become a dimension exactly?
How does time become dimension?
Yeah.
Well, what do we mean by dimension is the first question, right? So when you learn dimension maybe in school or high school, you talk about X, Y, and Z, and you say these are 3 dimensions, right? So the first way it counts dimension, because if you want to describe physics, you have to say not just where it happened, but when it happened. So you say X, Y, Z, and T. So if you don't like the word dimension, abstractly just think about it as 4 numbers. Where it happened, which is 3 numbers, and when it happened as 1 number. So altogether there are 4 numbers. And if for whatever reason we were blind, we couldn't see, that would be equivalent to what we mean by dimensions. In fact, it's preferable to be blind. The reason is that for higher dimensions, we cannot see it with our eyes. So we should be able to use the same more abstract definition of what dimension is as some collection of numbers. And that's good enough. So that's why time emerges. So even before Einstein introduced it, we knew there was a notion of time. But in the context of Newtonian physics, they're so different. The properties of space and time were so different. There was no sense in combining them into one object. What Einstein found was that they were actually have very similar properties, and it was necessary to combine them into one object. So that was why he put them on the same footing, time and space.
Okay, the doubt we had was about Fermat's least time principle. which basically says that between any 2 points in space, light takes the path which is not the least distance, but which takes the least time. So basically, even if you change the geometry of space, light should have not changed its path to go from one point of space to another, because it would take the least time from that. So isn't the principle of the Fermat's least time principle being violated here?
Least time principle. I mean, the distance and time would be the same if this light goes with the speed of light, right? So you're going with the least distance. That's geodesic.
But the distance is changing when you curve the space.
The distance is changing, and that's why the light will go a different path to find the shortest distance. In other words, let me say it differently. What we might think was, for example, x squared plus y squared plus z squared, the square root of, is a distance. That's the wrong notion of distance when the space is curved. So when I'm talking about distance, I only mean the correct definition of distance, which is what light would measure.
Oh, yeah, I get it. Thanks.
One last question.
Yes, over there.
Yeah.
Yeah, so you were speaking about extra dimensions to be microscopic. So when I take, I can imagine topologies like if I take a torus, even then I can go by two different paths where I don't come around. So what is the necessity for my extra dimensions to necessarily be microscopic?
Yes, so good question. So the reason it has to be microscopic is that it turns out that depending on the size of the extra dimensions, the gravitational force that we measure will be very different. In fact, if the size is very big, you have no gravitational force in the dimensions we measure. So therefore, the total volume of the space should be finite.
So does it mean that my, if I have a, are they inversely proportional?
Sorry?
Are they inversely proportional, like the size of my dimension and the gravity which I measure?
There's a direct relation between the volume and the force, yes. The strength of the force.
Okay, one very last question.
So you did mention that the physical properties could be same, right? But they could look very different. Is it possible in higher dimensions of reality that one object would permeate the other?
Permeate the other. What do you mean?
So I go back to a story by one of our early writers, Jayant Narlikar.
You want to use maybe the...
So Jayant Narlikar, he wrote a story called The House, and he says, in the higher dimension of reality, there could be another physical object that could permeate through this house. Is that possible?
Since I do not know about that, I haven't read that, so I cannot comment on that. So I'm not completely sure if I can give you a reasonable answer to the question. Sorry.
Okay, so maybe we should conclude now. And stepped into some geometry.
Black hole, don't go over there.
So before we thank Cumrun again, there's a small memento from
thank you very much.
ICTS.
It's great. Thank you. Thank you.
So thank you very much for coming for this special event, and let's thank all the speakers again. Okay, thank you. So the event's closed.